Okay, so one of the questions we are left with.
He left his folder in the cab, so.
Thank you. One of the questions we're left with is how close is close enough? We talk about a limit, we talk about approaching. How close do I really have to get? So I have this idea. That the limit of my function is some value. And we talked about x is getting closer to a, and f of x is getting closer to L, but that's very nebulous and weird and hand wavy. Let's try and nail this down a little more precisely. Let's do an example. Now I know that if I were to just attempt to evaluate this by plugging in x equals 2, I'd have a problem. I'd end up with an indeterminate form. Putting in 2 on the bottom gives me a 0, but so does putting in 2 on the top. 0 over 0 is an indeterminate, but I remember there's a way to work around that. This happens to factor nicely. Because that numerator is the difference of 2 squares. So if I cancel the x minus 2 part, everywhere except at 2, I end up with x plus 2. So instead of using this function, I can replace it with this one. And then this does evaluate. So I know the answer. The answer is 4. But this is undefined at 2. There's a hole in the picture at 4. If I graph this expression, I end up with this picture. And the problem is that hole in the picture. I'm never going to get 4. No matter what I plug into this expression, 4 is never going to come out. But I'm telling you the limit is 4. So now I can ask a legitimate question. How close is close enough to 4 to satisfy you? That's a real question, by the way. I want an answer. How close is close enough to 4 to make you satisfied? Yeah, I want a number. How close is close enough?
0.1 on each side.
Okay. So if I say I want to be within 0.1, I need a symbol for a small number. I've already used a symbol for a small number in X, right? This is a symbol for a small number in Y. I used the lowercase Greek letter delta for X. I'll use the next letter in the Greek alphabet, epsilon. And you said a tenth on either side, so I've made that epsilon 0.1. That means I want my Y value to be between 3.9 and 4.1, right? Within a tenth on either side of 4. Let me go back up to that picture for a second. What that really means is I should be able to draw a little belt. Where the top is 4.1 and the bottom is 3.9. You see how that cuts off a little piece of my graph? One of those intersections is to the left of x equals 2. One of those intersections is to the right. Of x equals 2. And now I have an answer. How close do I have to get to x to make sure I make your tolerance for y? As long as my x is in that little window down on the x-axis, then the y values will be in the piece of the graph you said was the right place to be. So if I am using Jack's 0.1, then that range down there at the bottom, that tells me how close to 2 I have to get. How close is close enough? You told me you wanted me within 0.1. Now I can go down and figure out here what those x values are, and I can tell you how close to 2 you have to aim. Now, I happen to know, in this case, the easiest way to do that is graphically. So grab your calculators, and let's graph 3 equations. I'm going to graph this equation first. Then I'm going to graph these two. And now, my goal is to make the picture we were just looking at on paper on this screen. So I'm going to go to the standard window, zoom option 6 to start. There's my two. See, they're really close together, aren't they? I'm going to need to look a lot more closely at what's going on right up here to see what's going on better. So I'm going to change the window. I only care about x around 2. So let's only go from 0 to 4 for the moment. I only care about y equals 4. So I really don't need to see all of the negatives. For the moment, let's only go from 0 to 5. And now I get this picture. There's my line. Here's the horizontal line at 4.1. There's the horizontal line at 3.9, and we see those two intersections, and we can even just barely make it out. There's a hole in the graph, isn't there? Right here, there's a dot missing. That's the hole. Now, if you've got a newer calculator with a higher resolution screen, you might not see that. This is one of the older TI-84s. It's got a lower resolution screen. If you've got the color edition or a newer version, screen may be better. You might not see the hole. That's all right. I know it should be there. And if I hit the trace button and I hit 2, it shows me y equals blank. I know there's no value there. I want to know where these two things intersect. I want to know where this curve intersects the line 4.1. I don't have to do that calculation by hand. I could set these two things equal to each other and do some algebra to solve that. But if I hit the calculate button, second trace, one of the things it will do for me is calculate intersections. And notice it asks you, well, what two things do you want to intersect? First curve. The first curve is the equation in Y1 by default. I hit enter. It jumps to the next equation in my list, which happens to be 4.1. You can put a little mark on the equation I've already used. I now hit enter again and ask me, oh, well, where do you think they cross? So if I go over here and I get close to where I think they cross, it'll make the calculation go faster. Hit enter a third time, and I get the x value where they cross. They cross at 2.1. Do the other one. Where does 3.9 cross this curve? What are the coordinates of that point of intersection? When you go to enter the second equation on the intersect button, you'll have to use the arrows, the arrow keys here, to make sure that you move instead of to Y2 down to Y3. Second, calculate intersection. The first curve is this one. But now I don't want to use 4.1. I hit the down arrow and it takes me to the next curve in the list, which is 3.9. Where do they cross? That's great. So we just figured something out. Jack, you said I need to be within 1/10 on either side. So I'm going to say, oh, well, then you need to aim for 2 and be within 1/10 on either side. I need to have an x value between 1.9 and 2.1. I found a little window. When I make a guaranteed statement now, if you want the y between 3.9 and 4.1, you need to pick an x between 1.9 and 2.1. Notice that happens to be a 1/10 on either side. That's actually the way I want to think about this. I want to think about it as how far on either side, right? I'm going to say that I can think of this as 2 minus 0.1 and 2 plus 0.1. And yesterday, I thought about this as x minus delta, x plus delta. So I'm going to say that my delta is 0.1. Now, you pulled 0.1 out of thin air, right, Jack?
Yeah.
Now, I don't know what we're doing with this particular equation, but let's actually give you a practical example here. I am making rebar to go into concrete to put up a building. The rebar needs to be 1 centimeter in diameter. But I go down to the factory and they're shoving hot metal through a die to shrink it down to 1 centimeter, pulling this bar thinner and thinner until it gets to be 1 centimeter in diameter. Now, some of those may be a little bit bigger than 1 centimeter. Some of them may be a little bit smaller. If it's bigger, I don't mind all that much. But if it's smaller, why is that a potential problem? It might not hold up the building, and that would suck. How close do they have to get to 1 centimeter for me? Now, maybe I say 1/10 of a centimeter is good enough. Maybe it turns out that I need to be within 0.05 centimeter. Maybe I need to be within 0.01 centimeter. I can't get any smaller than 0.99. I don't know about the tensile strength or strain load of rebar. I'm not a material science guy, but somewhere there's an engineer that tells me the minimum diameter is 0.95. I need to be within 0.05 of the correct diameter. The only thing I can adjust on my ring is its radius. How tight do I have to turn the dial? I have a very precise measurement now. You tell me how close you need to get. I tell you where you need to set the dial. If I can do this for any choice of number, then I can say the limit exists. I need to be able to find this delta for any possible epsilon value you give me. So if I want to be a real pain in the ass about this, I just say, well, 0.1 is a great number. 0.05 is a great number. I need to be able to do this no matter what the number is. The definition of a limit no matter what epsilon value you give me. There is some delta so that if I'm close enough to A, then the Y value is close enough to L. One of the teachers I worked with at the University of Pittsburgh, Dr. Alan Ho, used to say, really, you're making a bet with somebody who's a real pain in the ass. They're going to give you more and more and more numbers. You have to be able to do this every single time. And if they can find one number where it doesn't work, then that limit doesn't exist. Am I going to make you do this in general algebraically? Hell no. The goal here is to basically visualize this. Okay. On page 107 of our textbook, we have the following picture. It's a graph, f of x. I don't know diddly squat about this picture. But somebody gave me an epsilon. They said you need to be this close. And so we have an epsilon up and an epsilon down. And I need to make sure that I can get close enough to this spot to guarantee that if I use an X close enough down here, I'm going to be inside this little blue stripe. So what I need to do is I need to figure out, where does this cross? Where does this cross? Once I know what those values are, I start at A and I spread out until I hit one. If the closest one is on the right, I'll stop there. If the closest one is on the left, I'll stop there. It doesn't matter which one I hit first. But as soon as I hit one of these two, and you'll notice in this case, the one on the right appears a lot closer than the one on the left, yes? So I'm going to say, oh, as soon as I get this far, that's delta. However far I moved until I hit the closest one, that value is delta. And so over there in the right picture, we have a plus delta and a minus delta, and I can guarantee you, you're going to be inside the blue stripe if your x values are inside that little yellow vertical area. If you change epsilon, I still have to be able to do this. If you make it smaller, my delta is going to get small. If you make it bigger, my delta probably will get bigger. But I need to be able to do this every single time. Questions? Then let's try one. I want to do problem number 1. Right here. The first thing I need to do is I need you to tell me, based on my definition, I have epsilon, delta, A, L, Fx. I need to know what pieces on here match the pieces out of my definition. So, do we know what L is based on that picture? Or based on the expressions written above the picture? I think these might tell us easier. Which of the numbers up there is L? Zion. Yes, that's the part that has the L in it. It's f of x minus L, so this number is L. Our L value is 1. We're trying to get close to 1. The other thing that goes with the f of x minus L is either epsilon or delta. Does the epsilon go with that, or does the delta go with that? The epsilon, the first one. That's how close we want to try and get. Notice that this is 0.2 up, and this is 0.2 down. So I actually could think of this as 1 plus 0.2 and 1 minus 0.2. There's my epsilon reflected a little more clearly. Okay. Jump over to the other expression. There's only one number over there. What letter does that number go with? Ah, that's A. So that's this right here. Now I want to find delta. That's the goal of the bet. I give you an epsilon, you give me a delta. So I start at A, and I start to move out. Which vertical line do I hit first? The one on the left or the one on the right? The one on the right. I'm going to hit this one first. So that means that the distance from here to here is smaller than the distance from here to here. We can just actually compute both of them and then pick whichever one is smaller. This 1.1 minus 1 is 0.1. This 1 minus 0.7 is 0.3. I pick the smaller one. That's my value of delta. So in order for me to win the bet here, I need to be within 1/10 of the x value, 1. And then you're guaranteed to be within that horizontal stripe. Questions? Sometimes the picture won't give me all the information. What's missing here? Yeah, wait a minute. It's told me what f of x is. That's written right there. Okay, let's keep labeling. What else is up here on this side? What do these two numbers get labeled as? This is the E, and that makes this, and then there's delta, and that makes this great. So now I need to figure out how close to 4 I can get. Houston, we have a problem. They wrote question marks. That's not very nice. How am I supposed to find what those values are? Somewhere. Now the question is where? Yeah, I want to know where this curve crosses 2.4, where this curve crosses 1.6. How do I set up an equation to solve that? Algebra question. Is the 2.4 an input or an output? It's an output. So if it's an output, then it should be on the outside of the equation, the y value. And that means to find this x value, I need to take the square root of x equals 2.4 and solve for that x. Same thing over here. I need the square root of x equals 1.6. How do I get x? Square both sides. Now you can give me these numbers. What was that sign? Which one? No, I already have a square root. I got to get rid of the square root. Not multiplying. I'm squaring because I can think of this as x. The root is a 1/2 power, so I want a 2 for a power to cancel it out. So that means I need 1.6 squared. And over here, I need 2.4 squared. Sure.
5.6, 5.76.
Now I need to know which one's closer. Which one of those is closer to 4? The distance on this side is 1.44, 4 minus 2.56. The difference on this side is 1.76. So that's the smaller one. That's the value of delta. I think visually. I like the pictures. I keep thinking of what happens here as aiming. Okay, I don't care if you've played a video game that has a shooting interface, or if you've actually been hunting, or you use a gun or a bow or an arrow, or hell, if you've thrown a ball, you know how to aim. If I give you a target at the end of the room from me, I don't know, what's that? 30 feet? 40 feet, something like that? I'm going to hit the clock. I want to hit the exact center of the clock. I'll give myself a little bit of leeway. The bullseye is 2.5 inches across. I'm aiming my bow. How much wiggle room do I have with my hand? I have to hit a target 2.5 inches across. How much motion can I make? The 2.5 inches is epsilon. The motion I can make is delta. If I'm throwing a ball and I need to hit somebody who's 100 feet away, how much release difference do I have to be within an arm's reach, a yard on either side of them, so they don't have to move to catch it? If you've aimed for anything physically, you've done this. You just haven't thought of it in these terms. The size of my target is epsilon, the place I want to hit. Now, how much can I be off by? Let's actually do a physical interpretation. If you are building a computer chip, computer chips are made out of silicon. So you start with a circle of metal that has to be perfectly sized and cleaned, and then you lay your silicon on top of it. The size of the disk tells me how many computer chips I can make, because each computer chip is a certain size, and we're going to etch all of the little wiring pieces into the surface of the computer chip. Great. I need a circle whose area is 1,000 square centimeters, because each square centimeter is going to get its own chip. I'm going to put 1,000 of them on this disk. But the only thing I have control over is the radial cutter. Think about a compass that you use to draw circles, right? Those two little prongs, one side's got a pencil, the other side's got a pin. You pin it into the paper, and you draw your arc. The only thing you control is the radius. What radius do I need to make an area of 1,000 square centimeters? I like to draw pictures. As I said earlier, I'm a very visual person. So I want to draw a picture and then try and do some interpretation. Here's my circle. Circles have a particular radius. So the first part of this question, part A, what radius gives me an area of 1,000 square centimeters? I need an equation that's not here. I need f of x, right? If I'm doing a limit, I need the limit of some function. That's exactly the equation I need. The equation in this case, the f of r, is pi r squared. Because that's the area of a circle. So I set pi r squared equal to 1,000. So r squared is 1,000 divided by pi. Grab your calculator, and we take a square root. 1,000 divided by pi. Take the square root of that, and I get 17. Oh, crud. A lot of decimal places, right? I'm going to be a pain in the ass. I don't know how many decimal places I need yet. I'm going to write all of the decimal places I have down. Now, if I am perfect, I set this radius, I cut my circle, and I get exactly 1,000 square centimeters. I will never, ever claim to be perfect. So, part B, the machinist is allowed an error of plus or minus 5 square centimeters. Wait a minute. That's a change to the area, right? And the area is the output of this function. That's my epsilon. It's telling me how far above or below my target 1,000 I can be. So now the question is, how close to this do I have to get? How close to 17.841241116 centimeters do I have to get with my radius to be within the appropriate error and not waste a bunch of metal and have to throw out these discs? If I were drawing a picture, I'd have my graph of pi r squared. I'd have 1,000, right? And then I could be off by 5 above or 5 below. If I'm off by 5 above, what's the y value on this line? 1,005. If I'm below, so I need to know where these cross my graph f of r. Oh, I'm going to have to do this same exact solving again, once with 1,005, once with 995. Give me 2 new r values. And again, I'm going to be a pain in the butt. Write down all the decimal places at the moment. I do the exact same calculation to get r. And when I do my square roots, I get those numbers. How close are either of those to my ideal radius? My ideal radius is this number back here. So take the smaller one away from the larger one. What do you get? I don't know. I'm about to do it. Smaller one minus the larger one. Okay. Again, I'm going to write down all the decimal places they've given me, 044659. So on this side, oh 044659. What about on the other side? You don't actually have to hand type the numbers again. If you've got them in your calculator, you can use the up arrow function and go back and get the number you want. Hit enter, then minus, go back up and get the number you want. Hit enter, it copies it down. There's my difference for this side. 0.04454749. Okay. Which of those two differences is smaller? You now know how close is close enough. The smaller one is delta. Now that's in centimeters. So you have to be within 0.04 centimeters. That's 0.4 millimeters. That's really very small. At this point, I would even err on the side of caution and round down. So you said 0.045 something, right? I would round down and say 0.44044 something to make sure I'm even closer, to be within the margin, right? Because if I did 0.45, I might spill over a little bit on either side. Personally, I don't think I have ever tried to carve a metal disc of a precise area. I also don't work in a silicon chip factory, so I'm not going to do this. But this is a realistic rigged example. By the way, part C of this problem asked me to go through and identify all of the parts by the names they would have in the definition. So our f of x, our L, our A, our epsilon, and our delta. You can do these algebraically. I can do all of these calculations by hand. I don't think it's worth it, personally, to try and do all the algebra, especially as my functions get more complicated. If I want to do, say, a cosine as part of my limit. For example, one of the things we do, and I see a lot of you in this room using this, is we look at the difference as light is bent, as it changes from going through air to going through something else. What's something else? I don't know. How about glass? Light is bent as it slows down going through the glass on my glasses. In order for me to figure out the angle, I need a sine function. Snell's law, if you've taken a physics course doing optics, that's physics 2 here. They'll talk about index of refraction and how light bends. but I need to make it bend just the right amount to bring that light into focus on the back of my eye so that I can read the clock on the back of the room. Because without it, oh, that's a bad thing. But I need to know how much that bends. Figuring out the right angle would be this process. I know the angle I want it to reach so that the point hits the exact back of my eyeball in focus. When you sit in the optometrist chair and they keep flicking things back and forth, they're jumping between two different measurements to try and get closer and closer and closer to the right side. Everything we've done has been from both sides. I could do it just from one side and do a right limit or a left limit. I could do this as the L value is infinity. Remember we had limits that went to infinity? Well, then I don't actually get close to infinity. I just say, oh, at some point I'm absolutely goddamn huge. So the limit definition changes slightly in the way it's written. When I'm looking for a one-sided limit, you'll notice the delta is only on one side. It's either on the left side or the right side. And when I'm doing a limit that is dealing with infinity, I don't have an L anymore. I just have that my f of x gets really, really, really big for some big number m. And if it's negative infinity, then I switch this to be less than, and my m is a negative number. The idea here is that there is a level of precision that goes in to our definition. I have spent most of the time until now just waving my hand and like, trust me, it works. But this is how you can verify. You don't have to trust me if you can win the bet. Questions? I want you to be able to do these. I want you to be able to do them visually for the most part. I want you to be able to do the interpretations in real situations. I don't ask you to do this fairly often, but I am going to use this idea to make more definition to see if I can do what Chase wanted me to do and just plug the freaking stuff in. If that would work, I'd be happy about it, but I need to know when it's going to work, and that's based on this idea. I hope you all have a wonderful weekend. I will see you all on Monday. Enjoy the rest of your day.